Introduction and for inviting me to give a talk at this seminar series. It's been really fascinating so far. Today I'll be discussing work that's been done in collaboration between my institution, Pacific Northwest National Laboratory, Argonne National Laboratory, and the University of Washington on preserving structural motifs in machine learning approaches to modeling water clusters. This work is for the Exascale Computing Project, one of the flagship computing projects of the US Department of Energy, which has the goal to deliver exascale computing capabilities to national labs. The full project is participation from 15 of the 17 Department of Energy laboratories and involves approximately 1,000 researchers, scientists, US HPC systems companies, and project managers. Of this larger project, the specific work I'll talk about here is under the ExoLearn Co-Design Center. And our goal in the Co-Design Center is to develop scalable and sustainable machine learning frameworks through the collaboration of mathematicians, computer scientists, and the domain scientists who will actually use the software. And we want to create systems so that they run at the exascale and then apply our systems to real test problems to show how well everything works. The design problem we're focused on in this talk is molecular design. So in other words, how can we make new molecules or molecular systems with tailored properties? This process is general to any chemical design problem. We start with some initial system that we think we can improve upon. And somehow, I'll get into that, we generate a new structure. And then we score the new structure by calculating the property of interest that we are designing towards. We then assess that score and assign some sort of goodness value to say how well our design is. And this cycle is then iterated upon a number of times until we finally arrive at our optimized design. So keep this picture in mind as I go through this talk, because as you can see, there are a number of steps here, and the eventual goal is to put it all together into a large app that combines all these different steps to generate molecules. For our molecular design system, we're specifically focusing on generating clusters of water molecules. And we chose water molecules because our collaborators at University of Washington have generated a large database containing around 5 million clusters. So we don't have to restrict ourselves to methods that handle small data sets. And also this data set has a lot of geometric diversity, but very little chemical diversity. So we're focused on a very narrow region of chemical space, but a large area of structural space. And we want this because we're interested in designing clusters with tailored geometric properties, which I'll get into in the second half of this talk. And this database was generated through a Monte Carlo type potential energy search using a parameterized TTM 2.1F potential. All structures are minima on the potential energy surface and lie within 5 kilocalories per mole of the putative minimum for each size. In order to get the wider community involved in this work, we introduced a multi-representation data set made from the original database in last December's NeurIPS workshop on machine learning and the physical sciences. So I'd like to plug that data set for a second here. We've taken the XYZ files that chemists are used to working with and formatted the data into a structure that's readable by neural networks. So the XYZ files can still be found in the UW database website, but we now also provide JSON files and TensorFlow protobufs for easy ingestion and train validation and test splits for consistency through different processes. We then took that data a step further and provide 2 graph representations for each cluster. The XYZ files themselves are just the Cartesian coordinates, and so they don't directly indicate covalent or hydrogen bonding patterns. So we make these explicit in what we call an atomic graph, which is an undirected graph where each vertex is an atom and each edge is labeled as either covalent or hydrogen, depending on the bonding type. These are given in networkx format JSON files, and again, TensorFlow protobufs with the same train validation test splits. We also provide a coarse representation, which is a directed graph where each vertex is a water molecule and the edges are hydrogen bonds pointing from the donor to the acceptor. So again, these are given in the same multiple formats with the same splits for train test and validation. And we decided to provide all this to make working with this data set easy for chemists for whom formatting the data may be a hassle, and this gives an easy way to ingest it, but also for computer scientists who may not understand the intricacies of hydrogen bonding. So we've made those hydrogen bonds explicit in the graph structure here. Using this data set, we've outlined a set of challenge problems that feed into our design app. The first is property prediction. So given a cluster, can we predict the energy of that cluster? And we can go from either coordinates to energy or graph to energy. And then the second challenge is molecule generation. So given a certain cluster size of N water molecules, can we generate new structures that conform to certain geometric measures? As shown in this graph here, we can see the number of cycles will change as the cluster size changes. So first, let's talk about property prediction specifically. We examined the coordinate to energy problem using one of the leading architectures for predicting properties from molecular geometry, which is SCHNET. SCHNET's a continuous filter convolutional neural network, and it's unique in the sense that it learns representations of the neighborhood of each atom through filters and then performs convolutions over those learned filters. And then these atom embeddings are passed through an MLP, which generates a contribution to the energy from each atom. And then finally, that is summed to get the full energy for the full molecular system. Let's now take a look at how SCHNET does at learning the neighborhoods for our water cluster data set. Here we have a system of 4 water molecules, each with identical neighborhoods. You can see the hydrogen bonding goes in a square here. So they're all accepting 1 hydrogen bond and donating 1 hydrogen bond. And I've plotted here the embeddings of each atom after the second interaction layer. So this is after SCHNET has learned the representation for the neighborhood of each atom. And then we can take the cosine distance between each embedding to see how different those embeddings are. So looking at the cosine distance in the embeddings of the oxygen atoms, we can see that they're always 0. So we can see O7 to O1, 0, O10 to O1, O4 to O1, all 0. So this is exactly what we expect because all 4 oxygens are equivalent here. And if we look at the hydrogen atom embeddings, we can see we have 2 different neighborhoods, one for the hydrogens donating to the hydrogen bond and one for the hydrogens not involved in hydrogen bonding. Excuse me. So we can see if we compare H12, which is not involved in hydrogen bonding, with H2, which is also not involved, we get a cosine distance of 0, which is what we expect. Now let's compare H12 with H3, which is involved with hydrogen bonding, and we see we get a value of 1.19. So the neighborhood for H12 and H3 is different. And then if we want to compare H3 with H5, for instance, which should be equivalent, H5, H3, and it is, we have a cosine distance of 0. So we can see that for this very simple case of all equivalent water molecules, the embeddings are accurately reflecting the atomic neighborhoods. So let's look at a more complicated case. We have 5 types of atom interactions here. We have hydrogens participating in hydrogen bonds, hydrogens not participating in hydrogen bonds, oxygens participating in 1 hydrogen bond, an oxygen participating in 2 hydrogen bonds, and the oxygen participating in no hydrogen bonds. So if we look closely at this cosine distance matrix, we can see that there are more than 5 neighborhoods described. To make a long story short, the HH cosine distances we see change depending on the number of hydrogen bonds going to its partner oxygen, which means that the encodings for hydrogen depend on the oxygen neighborhood. And this is good. This is showing us that more is being accounted for than the direct bonding interactions, and that the embeddings are taking the wider neighborhood into account. So that the neighborhoods are well represented, let's see if our prediction of the energy is accurate. So we trained SNET on a subset of our database because SNET is quite computationally intensive, even when trained across multiple GPUs. And we found that over a range of cluster size, we see low absolute errors per water molecule of around 0.002 kilocal per mole, even on cluster sizes not included in the training set. So we only trained on clusters of size 11 to 29, and then we tested on clusters of size 10 and 30 and saw equivalent errors. And so this is very encouraging. It shows that we can train our network and use it to predict the energy of larger size clusters that we did not train on. So this solves the coordinate to energy challenge in the score design step if we want to work in coordinate space. But what if we want to work in graph space? So we implemented a simple message passing neural network and trained it on the full splits for the atomic graphs given in our HydroNet database. And even though this network was trained on a larger data set than we used for the coordinate-based approach, the errors were about an order of magnitude higher, and the error was even higher for small clusters with less than 10 water molecules. So MPNNs only consider interactions between atoms with connected edges, so either covalent or hydrogen bonded atoms here, and not the wider neighborhood like we observed with SNET. And so what this tells us is that there is more potential for graph neural networks, and there's more work to do to get graph neural networks to have the same performance as state-of-the-art coordinate-based neural networks. And this is an ongoing problem, and there have been some advancements in accounting for the global graph structure, such as done in position-aware graph neural networks, but we still see a lot of potential for growth here that our dataset might be able to help with. But for now, let's move on to molecule generation. So this is the bulk of the design process in our app, where we want to create new structures with tailored geometries that are also low in energy. So let's recap how the original database was generated. Our collaborators at the University of Washington, along with their collaborators at Jawaharlal Nehru University, use Monte Carlo temperature basin paving, which applies a parameterized potential for stochastic sampling of the energy landscape. And so each Monte Carlo step lands somewhere on the potential energy surface and is then relaxed to the nearest basin. So in the ideal situation, you take a big enough step to move to the next basin, but often the steps are too small and you end up relaxing back down to the minimum you just explored. Or the steps could be too large and you actually miss minimum in your search. And in this case, we've missed the global minimum. So this process requires sampling hundreds of thousands of structures for each cluster size to land upon the lowest energy. And this is the reason why the database is so large, because they did all the sampling. And we're working to streamline this process, doing the sampling with reinforcement learning. So reinforcement learning involves training models to make a sequence of decisions that lead to a certain outcome. The algorithm uses trial and error to come up with the solution to the problem. So we really have the algorithm making its own solution to the problem we give it. And to move the algorithm in the desired direction, the algorithm is given rewards or penalties for the actions it performs. And this leads to kind of a game-like situation where the algorithm is trying to maximize its reward, minimize its penalties, while figuring out how to solve the problem we've given it. And in fact, many of the initial implementations of reinforcement learning were actually teaching computers to play games. So very famously, the reinforcement learning algorithm AlphaGo was the first computer program to defeat a Go world champion, as we see here in 2017. And there's actually a very interesting documentary about this algorithm and about the game that was played. So you might want to check that out if you're interested in reinforcement learning. But this game-like situation leads the algorithm to learn the best possible moves to take over time to maximize its reward. And so it can experience thousands of parallel runs all at once when using sufficiently powerful computers. So it can essentially play tens of thousands of games to try and learn how this game works. And it's really up to the model to figure out how to perform the task to maximize the reward. So it can end up showing very unusual but sophisticated tactics to reaching its goal, things humans wouldn't normally think about. Now let's see how we can generate low energy structures of water clusters using reinforcement learning. So ExoRL is another project in the ExaLearn Co-Design Center, and it provides a Python-based framework to develop RL environments. And the goal in building up RL capabilities isn't solely to examine water clusters. We want to produce a code that can be easily shared between different projects, even projects outside of the chemistry domain, because this can be a very generic algorithm. So each box in this diagram can be tuned individually to amend the code to the specific problem in question. And other things can be shared between different projects if necessary. And so overall, our reinforcement loop covers the design and scoring process to produce a new low energy structure. And let's look at the pieces in this loop. So the action is simply some structural change we want to implement. This is the rules of the game. What kind of moves is our algorithm allowed to make to accomplish its goal? And the policy is the mechanism that implements that change. So our policy here is a differential dynamic programming policy, and this is a neural network that is continually trained during the RL run. So at first, our policy is just taking random actions, and as this cycle continues, it takes a random action, gets a reward, and then is actually being trained during the RL run, and the data for that policy network is being generated during that RL run. So it starts out with random moves and eventually learns which actions are best to take. So after we take an action, we pass the new structure through the environment, which here is just a simple property calculation. And we are starting out doing this in coordinate space. So the environment is a relaxation and energy calculation using that parameterized TTM 2.1F potential for water. And so this gives us a structure that corresponds to a minimum on the potential energy surface and the energy at that minimum. The reward is in the metric that drives the policy, and it tells the network if the changes it made were good or bad, if it's moving us towards our goal or away from the goal. And so initially, we're just simply taking the negative of the energy difference, and this tells the policy whether the move it made reduced the energy, which is good, or if it increased the energy, which would be a negative reward, and that would be bad. So over time, we're taking actions, getting rewards, training this policy network, and the algorithm is really learning what action should it take to reach its goal of having a low energy structure. So what are the moves we can make? For the initial implementation, we're making just a series of very simple moves. First, the policy chooses a water molecule to manipulate, just one for now. And then it chooses a rotation about the C2 axis. And this rotation was restricted to between 75 and 105 degrees. And this is to match the Monte Carlo temperature basin paving moves that were made in the generation of the database. And then finally, we also have a small translation from 0.3 to 0.7 angstroms, again, to match the moves that were used for the Monte Carlo temperature basin paving. And so these are just very simple, right? One molecule being rotated and translated a little bit and then relaxed back down. And the moves don't have to be restricted to this. We could take a group of water molecules and rotate and translate them instead of just going one by one, or we could even move to graph space where we indicate the formation of new hydrogen bonds and actually direct the graph in different ways that way. But let's see how these XYZ coordinate-based actions work. Along with, remember, our reward structure is simply, it gets a reward if the next step is a lower energy than the previous step. So let's see how it works. We start out looking at water clusters of size 10, and we start with the highest energy cluster of that size in the database, which is shown here, kind of almost like a boat-like structure. And we allow 10 steps for each episode. So what this means is that the algorithm can make 10 moves to get to the lowest energy one that it can find. And so after about 1,000 episodes, each with 10 moves each, we end up with the 9th lowest energy configuration out of over 11,000 intermediate structures. So it moved from this high energy, not very symmetric structure pretty quickly all the way down to this more symmetric, lower energy structure. And this only took really 30 minutes to move from the high energy to the 9th lowest. And well, there are a few things we could do to improve the search. So there are different hyperparameters we could look at. For example, the length of each episode could be increased so that the algorithm would have more than 10 moves available to get to the lowest energy. We could probably try going out more episodes because that trains the policy network more each time, so it learns the best moves to make. We could improve the representation of the clusters in the policy network by providing better embeddings closer to what Schneck gives for each atom. So if we really represent the neighborhood well, that could help the policy network decide which moves to make. And so these are all things we plan to do in the future, but I just wanted to give you all kind of a taste of what this algorithm is doing right now. So one of the most interesting things we could do besides all the little tweaks I spoke about earlier is we can enhance the reward function to be more than simply just minimizing the energy at each step. So the reward function really drives the policy, which drives the structural change. So it's really this reward function that's steering the learning process. And we aren't restricted for looking at the lowest energy structure, right? We can add structural properties of interest. For example, if we want a very cubic structure like shown here, we could add a reward for when tetramers are present, or when pentamers to get this other structure, or hexamers, whatever. We could give a reward for more hydrogen bonds present if we want to find a very highly connected network. Essentially, if a property can be described by a scalar value, it could be used to steer the learning process. So anything, any property you can turn into a singular number can be used to drive the algorithm. But and also I should say that the reward can also be directed towards multiple properties, right? We could do something like a linear combination. where we want to minimize the energy and also go towards some kind of geometric signature. But one of the big caveats here is that scalar rewards can have unexpected consequences. For example, let's say we have a goal to have a child clean their room, and our reward is the area of clean carpet. So if they've done a good job, they have a large square area of clean carpet. But the child may just learn to throw all their toys on the bed rather than put them away, right? Because that's going to give the same amount of clean carpet as whether they put them away on the shelves in the toy box. So the reward really needs to be carefully thought through and tested, because the algorithm will take what it sees as the best steps to maximize its reward. And it has no idea of the task you want it to do besides what the reward tells it to do. So that's something that needs to be really thought through and tested very well. So overall, I hope I've shown you the usefulness of our multi-representation data set called HydroNet, and how it can be used for property prediction in both coordinate space and graph space. And so there's still a lot of potential for improving property prediction with graph neural networks, and we really believe our data set can help advance that effort, especially when it comes to non-bonding interactions or like hydrogen bonding interactions that aren't explicitly covalent bonds. And I also hope I've shown the novelty of using reinforcement learning to generate new structures with tailored properties. The work is still ongoing, as you can see in the presentation, but keep an eye out for something in the coming months towards that end. And I'd like to thank my collaborators at the University of Washington and Argonne National Laboratory. And please check out our landing page for HydroNet on the GitHub, so it will show you how to get the data sets, and you can also see the code we use to make the MPNN and the Schneck code we used earlier in this talk. And we also present here, the archive link is our paper from the NeurIPS workshop that describes this data set in more detail. So thanks everyone for coming out today and listening. And if anyone has any questions, I'm happy to answer them.